Welcome back. This lesson we're going to be looking at how to find the area under a graph. So if we think of any graph at all, there's going to be an area that's enclosed by that graph and the x-axis. So if I wanted to find this area here, how could I do it? Now there's a couple of different ways. And the first way we're going to look at is what's called the left and right endpoint estimate. So let's take a look at this function here, y equals x squared plus 3. So we want to find the area between 1 and 3. And you notice here that it doesn't make a nice regular shape for us. It's got this curved part here because it's part of the parabola, and then it comes down here. So what we do know is the area of rectangles, length times width. So to find the area of this rectangle at the moment, I could say here my height multiplied by my width. So if it goes up 4 units here, I see it's got a height of 4, goes across 2. We could say that this blue rectangle has an area of 8, and so we say that's an estimate. And you go, well, look at all this white space here that you're missing. So what we do is we take points along the graph here, and we draw rectangles. Now if we increase the number of rectangles between, we're looking just for the area between 1 and 3, if we increase the number of rectangles, let's put another rectangle here at 2, we can see now that this rectangle has a height of 4, goes across 1, so this area here would be 4, and then this one here at the point x equals 2, it's got a height of 7. So we go, well, 4 plus 7 times 1 would be 11. So we say, well, this area is roughly 11. As we increase it to 3 rectangles, we can see that area is approximately 12.15. And if we increase the number of rectangles so that the width of each rectangle is smaller and smaller, or the space between them is smaller, notice that we're going to get closer and closer to the actual area. And we say at 20 rectangles, you see these are little tiny bits of white bits that we're not actually accounting for. So the area is about 14.27. We would call this the left point estimate. Because if we look at the rectangles, the left point of the rectangle is a point on the graph. So to find that, we would have to use the height, which would be the y value of the original function at each of these x intervals. So if I was taking it at 1, 2, let's even go a little bit simpler here. Let's just look at 2 rectangles. So I've got a width of 1, then I'd have to go, well, this width 1 and this width is 1, so it's always going to be 1 times the value of the function at each of these x values on the left point. So the function at 1 times 1 plus the function at 2 times 1. And we can see here our points. Now as that increases, the distance between these 2 points is always going to be the same. So in this case it's a quarter, so each of them are going up by a quarter. And the height here is a function at 1. This would be the function at 1.25. Then the function at 1.5 would be the height for each of these. So we'd multiply each of those by the width and then add them all together to get an approximation for the area. So, recapping, as we got up to 20 triangles, we're looking at roughly 14.27. So that's when we had 20 triangles. Now let's go back to our workspace here, and let's write down what we know from that estimate. The function was x squared plus 3 between 1 and 3. We're saying is approximately 14.27 when we had 20 rectangles. How do we find that exact area? So now we're finding the exact area. Okay, whereas in this was an estimate. And like I said, there's a couple of different estimates you can do. You can do a left and right, or you can also try and draw trapeziums there to find a little bit more closer to the actual value. But let's say I wanted the exact area. What we do is we find what's called the definite integral. So we still use our integral sign, and what we do is we put our points that we're trying to find between our x values, we're trying to find it between the point 1 and 3, we put here. And we write x squared plus 3 dx. So what we're trying to do is find the integral for this function at 3 and then the integral at 1. So when we look at our graph, the integral is actually finding the area under a graph. So if I found the integral at 3, it would be finding this whole area all the way down to 0 there. So then I have to subtract the area when it's at 1. And that will leave me with just the area between 1 and 3. So let's have a look how we set out our working out. We'd find the antiderivative of this. So again, just to recap, we add 1 to the power, so to become x cubed, and we divide by that new power. We can integrate each of these terms separately, so plus 3 is the same as plus 3x to the power of 0, so we add 1 to the power, we get plus 3x. Now, this is where it's a little bit different. Normally, we would do plus c, and then, like I said, we'd substitute in when it's at 3. So we're going to use all this at 3, and then we'd subtract all of that again, x cubed on 3 plus 3x plus c when it's at 1. Okay? And what's going to happen is the c's are going to cancel off. So we don't have to worry about them because it doesn't matter what the constant is, we're going to be subtracting it at the end, so it'll drop off. So the way that we write this, we use these square brackets here, saying this is our antiderivative, and we put in 3 to 1. So that means we substitute in the value of x equals 3. So we'd have 3 cubed on 3 plus 3 times 3. And then we subtract when it's at this lower value, which is 1. So we'd have 1 cubed on 3 plus 3. And let's find out what this equals. So 3 cubed would be 27 on 3 plus 9. And we're going to be minusing 1/3 plus 3. So we'd have 27 on 3 is 9, so we'd have 18 minus 3 1/3 would get us to 14 2/3. And we see at the top here, we were getting closer there, 14.27, and that was with 20 rectangles. We could keep going infinitely long, so this would be your exact area, 14 2/3. Let's have a look at one more example. We've got x plus 1 all squared dx, and we're trying to find between negative 1 and 2. Now, x plus 1, if we think about what the graph looks like, it's going to have a turning point at x equals negative 1, so it's going to look like that. So the area between negative 1 to 2, we can see is going to be this area here. That's what we're trying to find. Now, you don't have to sketch it first, but I like to do it because you do run into problems when it goes below the x-axis. You're going to have negative areas there, and we'll look at that next lesson when we looked at the signed area. But for now, we're just going to look at when it's always above the x-axis. So, repeating those steps from our last example, we do the antiderivative. Now, negative 1 to 2. I'm going to expand this out, just make that x squared plus 2x plus 1 dx. So the antiderivative of this would be x cubed on 3 plus x squared. The 2's would cancel off, divide by that new power, plus x. And I'm going to be doing this between negative 1 and 2. So let's sub those in. 2 cubed. I'll do a different color so you can see where they're coming from. That's just our x values. Plus 2 squared plus 2 minus all of that again when x is negative 1. So negative 1 cubed plus minus 1 squared plus minus 1. So following through, 2 cubed is 8 on 3 plus 4 plus 2 minus negative 1 cubed is minus 1, so it's minus 1/3 plus 1 minus 1, so they'll cancel off. So we end up getting, what would that be? That would be 6, so 4 plus 2 is 6. 8/3 is the same as 2 2/3, so we'd get 8 2/3 plus 1/3, so it would be 9. Okay, now there is an easy way to do this on our CAS. Let's pull that up and have a look. So from our main section, we go up the top to action calculation, and you've got your derivative, your antiderivative, your integral sign. The other way of getting there, if you go keyboard math 2, we can see we've got this integral sign here. So just below I, next to the limit here, and we can actually type in all our values. So up the top here, we had 2 to -1, so I put a 2 in that top one. Go down the bottom, put my -1, and my function was x plus 1 all squared, wasn't it? X plus 1 all squared. And then don't forget to put the variable you're differentiating in terms of, which is x for this one. Hit execute, and you see the answer is 9. Alright, that's how to do it by hand. So you find the antiderivative. Remember, the c's are going to cancel off, so you don't have to have a constant in here. And you're going to substitute in your upper value here for x, which was in this case was 2, and then subtract when you substitute in x is the lower value, which in this case was -1, and then tidy it all up algebraically to find the exact area. Alright, as you can see here, you might get some fractions and stuff in your answer, but that is always going to be the exact area, whereas in the estimate, we'd have to add all these rectangles. Now, if we could increase this, it should be getting closer to 14 2/3 as we found. So you can see there's still some spaces in there, but that is how you find the area under the graph. So that should cover you for 21A and B. Next lesson, we're going to look at when the graphs actually go below the x-axis. What do we do when we have positive and negatives? Do they cancel each other out? We'll see you then.